Hello. Um, Here again to talk to you a little bit about measuring molecular weights. And this is sort of a simplified version of it because it's intended that this go along with actually doing some molecular weight measurements. And the molecular weight is very important for polymer science because strength and many other parameters, viscosity all the way out to even color in some cases, can depend on the molecular weight. And it's a very heavily studied thing and means lots of people are employed making these molecular weight measurements. So this information, more information, can be found in almost any book, but I'll always call out to your attention the AppTech virtual book, which is online. Of course, the quality of the virtual book chapters varies a little bit, but I think this one is more or less in good shape. So anyway, I thought I would integrate in a little bit about PowerPoint design. Some of this is a matter of personal taste, but there are good guidelines that you can follow. This one here, the visual display of quantitative information by Edward R. Tufte, is a classic. This is considered by Amazon to be one of the top 100 books of the 20th century. Well, that was a while ago, the 20th century, but still, that's a laudable achievement to be in one of the top 100 books. So this is a little bit about how to arrange data in some convenient fashion for your readers. Now, a cardinal rule for me, and I hope I always obey it, but I sometimes do lapse, is that there should be a slide number on the slide. This helps during Q&A sessions later at the talk. They can say, hey, would you go back to slide 7? That's where I began to get confused about something. I think sometimes you can have very tasteful animations. Here's one that's sort of dated by style, but anyway, not too complicated. And it shows the diagonal arrow, and that's to remind me to tell you that if you have a vertically aligned bullet list, that's kind of hard for readers to read, especially the further away you get from a screen. Your eyes sort of need guidance, and they work kind of diagonally well. So this is actually called visual tension. To put these are equal bullet points here, but notice that they're not really, in a bulleted list. There's no bullet. It's just the visual tension and to separate them. It's important to me, and I think most experts agree, that the top of the slide have a complete idea. I used to insist on complete sentences. This is a complete sentence. It has a subject and a verb and a period at the end even. But you don't need that. Sometimes you can have a complete idea. But what it should not say is, it really shouldn't say something like DSC results. Okay. I think that's, it'd be much better to say DSE confirms an enthalpic transition. Why? Well, because sometimes somebody is arriving late to your talk, usually at an international meeting, or you will have people who do not hear very well in English. They may not understand what you're saying. If you're at a foreign meeting, you may be attempting to do that in Spanish or something, or in French, and then they may not understand what you're saying. But here, whether they arrive late or just have some other problem understanding what you're saying, the basic idea is there. I have had people say that this is not a good idea because it detracts from the listener listening to what you say. So if it's really important that they listen to what you say, bully for you. I think you want to get the point across. So anyway, that's a little bit about that. Here is a tip that was given to me once by some experts. Not often, but occasionally you can put in something funny or strange or just, kind of out there to keep the bored listeners thinking. Just a little something for them to latch onto. If I was giving this talk to a bunch of faculty, I can guarantee you they would all, to the last man or woman, they would all claim that they are already experts in PowerPoint and tune out immediately. But they might notice this little tidbit here, which has to do with the subject at hand, which is gel permeation chromatography. This shows the initial unemployment rate for claims in 2020, and you can see when that pandemic hit, my goodness. And we're almost at an exponential decay. It looks like we should probably fit that to an exponential decay. But look at this at the bottom here. It says unemployment for GPC experts. Well, that's not what this plot is, but I'll bet you there basically was none. Okay, this technique that we're going to learn about, gel permeation chromatography, and other polymer characterization methods are usually in high demand. Well, I like this quote from a long time ago. Goodness, that is a long time ago, isn't it? And I was out at Dow Chemical, and I was giving a talk, and I talked a little bit about absolute measurement of molecular weights by light scattering and other methods. And she jumps up as a manager. She jumps up and says, "You cannot measure absolute molecular weights of polymers." And this was a surprise to me, but her underlings, the people in the audience that worked for her, just sort of rolled their eyes and bit their lip, thinking, there she goes again. Sometimes the management is not the brightest people. But even in 1983, you did not have to measure absolute molecular weights, but you almost always could have. Correct in 2005 or 2020. I should change that, shouldn't I? That's right. It's almost always essential to measure absolute molecular weights. Okay. There are groups here that really struggle to do it because of certain problems with their polymers. We have many polymer people here making basically tiny polymers. We can almost call them oligomers. And they tend to be highly colorful as well. And this can give us fits in measuring absolute molecular weights. So an absolute molecular weight is one that's tied to thermodynamics or to the stoichiometry of the chemical reaction, which is given to you by a technique like spectroscopy or NMR maybe, or FTIR maybe, or matrix-assisted laser desorption ionization time of flight mass spectroscopy, which is called MALDI for obvious reasons. We'll talk a little bit about those things today, but for now it's important to know that there are calibrated molecular weights, is what this manager at Dow was trying to tell me. That's all we could do is calibrate them. And then there really is absolute measurement of molecular weight. So how would you analyze polymers and nanoparticles for polydispersity? That's a kind of typical question. And easiest equation in the whole lecture, this is not a lecture, this is not a equation-prone lecture, would be that size exclusion chromatography is the same as gel permeation chromatography, is the same as gel filtration chromatography. Now, this word GPC, this acronym GPC, is increasingly less used. The current favorite seems to be size exclusion chromatography. But for my money, they're still the same, and I can actually say GPC better than I can say SEC. So go with GPC. All right, so let's begin this with a riddle. Okay, so a hurricane comes, many trees fall over, and they bend into the river. And unfortunately, a cow and a dog fall into the flooded river. And they're on their way to the ocean in the rapidly raging waters. Which one gets there first? So I'll give you a little while to think about that, but then I'm going to just tell you that the answer is that the cow gets there first. And the reason is that the dog can fit into interstices between the branches of this tree, and the water flow is greatly slowed down in that area. Now, you could say, well, the dog can grab onto and hold it with its paws. Well, yeah, sort of, but they don't really have opposable thumbs quite like humans do. So it's really that the dog can work its way into the tree zone, and in that tree zone, the water will be flowing more slowly. Eventually, it'll carry the dog out, and then he'll wind up in another part of another tree, maybe. But the cow's going to go racing by. It's going to go in the raging floodwaters. And if you don't believe this, you can just kind of simulate this by, next time you're out hiking, find a branch or cut yourself a branch and put it in the water of a nearby stream, and you'll see that the leaves and stuff slow down when they go into the zone where the tree is. Okay, that's just the facts of the matter. So this is what we try to set up in gel permeation chromatography. In GPC, as when throwing a cat through a tree, the big things come out first, okay? So little cat's gonna latch on and a big cat's not. So what happens here is big polymer and little polymer. The little polymer just sort of gets inside of this porous network that we build inside of the column. This is meant to be a column flowing through these gel beads that are made. And the big ones work their way around. It doesn't seem particularly obvious in 2 dimensions that these big ones are going to be able to work their way around. But if you imagine this in 3 dimensions, you can see right there. That's going to be an interstice, and a polymer can work right through that interstice. And over here will be some more. Whereas the little one is small enough to get caught up inside of this bead, and it just slows it down, okay? All right, so it's actually thought that what really controls the elution is the particle volume. That's if things are going well. You could worry about things like, well, what if my polymer sticks to the column? That's not good. And that can be a problem, and then you're not in a size exclusion system anymore, okay? So what you really want is that the thing that controls the rate at which something comes out of the column, people say the rate at which things elute from the column, E-L-U-T-E, that elution volume for the polymers is less when they're large, and longer elution volume. It takes more flow of more material through the whole system before the little ones come out. So the big ones come out first. That's the main message. Well, this is kind of a cartoon diagram of what one of these systems works like. And here I called it SEC. And it's a simple experiment. It has pumps in it and stuff, and they break and leak, and so there's problems, and we've been challenged with some of those lately. But I think we're good to go now. And what you start with is a solvent, a bottle of solvent. And you try to get the gas out of the solvent. In any solvent, there's dissolved gas. And you want to get that out because you're going to pump it. And then when it comes at the end of the column, it could bubble on you. But also, the dissolved gas changes the refractive index of the solvent. And we want to have that be some nice constant thing, because what we're going to do is we're going to have a pump. This is my idea of a pump. And it's a pump that's you should think the size of a toaster. Okay, it's not like a civil engineer's pump or even a chemical engineer's pump. It's a smallish pump, and it's designed to work at precise flow rates, typically 0.75 mils per minute or something like that, maybe 1 mil per minute. And it's going to do that 1.0, probably 1.00 mils per minute. And it's going to do that for a very long time, and then it's going to break. You're going to cry. But you're going to pump this material out of the solvent. And then you have a system that lets you inject a sample. So the pumped solvent comes into this system, and your sample comes into the system, and you sort of throw a switch, and your sample winds up going through some columns. It's narrow bore tubing. You'll see when we look at this in the lab, you'll see that it's very narrow bore tubing. And then it goes through 1, 2, and 3 of these columns, typically 3, but it can be as little as 1. Okay, so your polymer solution is going to work its way through here, and it's just going to be a spike. It's going to kind of come through because you're going to inject, you're going to load your column on your sample onto the column, and then it's going to be followed by more solvent from the pump, and it's going to go into this DRI detector, which we have studied the DRI detection already, right? A split cell type system. But this one is electronic, okay, so that it records. And when your polymer comes out, usually the refractive index will be very slightly higher for the polymer solution than it is for the running solvent, okay? And you're going to collect how long it takes for a series of polymers to come out. And this is what it's going to look like. You're going to have this thing here is the elution volume. Let's see if I can actually write that word down now. See that the thing doesn't want to cooperate very well. There we go. This is elution volume, and typical would be, about 30 milliliters. It varies, and over here would be like 0, of course. Okay. And you could run this experiment for very high molecular weights, and as I told you, they come out at low elution volume, and they just come squirting right out. Okay. And then you could run over here and inject a lower molecular weight polymer. Okay, and it'll get caught up on the gel beads and come out much more slowly. And then you can run some in between. Now, notice that all these points here, it takes 2 data things to make a point. You need to know what the molecular weight is. Okay. So that when you're running a regular GPC, that known molecular weight comes from a known calibration standard. You actually, we buy at great expense materials that have been, tested and had their molecular weights determined analytically and absolutely. And if you run those through, you'll see how the high molecular weight ones come out very quickly, and the low molecular weight ones come out much more slowly, okay? And notice that the resolution, the ability to separate the molecular weights is poor in this region here, okay? Above a certain size, It doesn't matter if it's a big cow or a little cow, it's not going to get into the branches of the tree in the river, right? It's going to go sailing around, come out fast. So you have sort of poor resolution. All the big ones come out at some, ridiculously low volume, and you really cannot separate them. But it probably, is good separation between this one and this one I have, and this one and this one even. Because I can measure that elution volume, typically with 1 or 2 place precision. And you'll see. Okay, so this is what would happen when we run our unknown. So the little green dots are running known molecular weight polymers from a calibration standard set. And then you might run your normal polymer that you made and the blue line, and you would get sort of a peak that came out like this. This blue peak should be looked at as like lots of points. It's like it's almost a continuum of points in here, because macromolecules are discrete objects. You have a polystyrene of molecular weight 10, that's a molecular weight of DP10, that's 1040 molecular weight. DP11 would be 104 plus that, so that'd be what, 1144. So, there is a discrete separation, but we usually cannot separate that finely. It is difficult to separate a 10 mer from an 11 mer. It is difficult to separate 100 mer from 105 mer. And remember, we're going to go into the thousands. So can I separate 1,000 mer polymer from an 1,100 mer polymer? Well, probably not. Not with impunity anyway. There are people who can do such things. But it's really this blue curve here actually is, representing discrete molecules, just that it's sort of fuzzed out. We can't really resolve things that finely. But anyway, that's our measured unknown material, and you see that it has some molecular weights that seem to be whatever this number is here. And then it seems to have some molecular weights, that are, whatever that number is. And how you know how much of each one is given by concentration C. And as you can guess, that concentration C is going to be, delta N from the DRI detector times dC dN. All right, so this is not going to work if dC dN is infinity. If dN dC is 0, there is no variation of refractive index with concentration, then this isn't going to work, and you're going to need some other kind of detector besides this differential refractive index detector here. And they make those. They make fluorescence detectors. They make ultraviolet visible absorption detectors. They even make a detector that sort of mists the sample as it comes out. It dries it out and weighs the stuff and tries to measure it. Turns the solution into evaporates the solvent and tries to measure the kind of powdery mist of dried polymer stuff that's left behind. So there's all kinds of schemes for measuring these concentrations, but almost always it's a DRI detector. Okay, and so you can then associate each point on the blue curve can give you a concentration and a mass concentration from the height of the blue curve, and the mass from the corresponding molecular weight that came from your calibration curve. Okay, so this is getting kind of messy. Let's go and discard those and then open it up again. Okay, so green thing is your calibration curve, and it is only VE versus log M. The blue thing is your unknown curve, your polymer that you're trying to test. And you effectively reflect a point on the blue curve off the calibration curve. You keep the Y signal to represent your concentration, and you bounce the elution volume off the calibration curve. So that's going to look like that when you're done. Okay. See, you're going to now have your concentration curve kind of got over here, and your molecular weight curve here. So see, this is our low molecular weight stuff that came out last, and so that peak is now here at low molecular weights, and the main peak is came out a little sooner, and so that's at a higher molecular weight. That's how it works. And then you just sort of usually rearrange it because people really want to know something like, what is the concentration as a function of the weight? Okay, so this is just sort of rotating that curve around. So that's the process. The process is to calibrate the column set and then run your sample. And to calibrate the column set, you have to have known calibration standards. Somebody had to measure those molecular weights. Okay, so here it is again. GPC, first make map, calibrate, then you follow it. This is the point that we have to make here. I do have to point out, because people often do this wrong, that the DRI signal is the signal above the baseline. This DRI signal is this. It is not that. Just cross that out. It's not that. Okay, so now rather than cross it out, we'll erase it. Just erase it. Okay. So this is what you want. You want the height between the baseline and the actual curve, and that's your DRI signal. The DRI signal, as I said on the previous slide, is proportional to the concentration. Wow, looks like we're having trouble. And it's just slow. Grams per milliliter. The DRI is cents, grams per milliliter. Okay. And so you have something proportional to the concentration, even if you don't know DNDC. DNDC can't be zero. It's nice if you know DNDC because then you can actually get the real true concentration. But if you don't, you still have something very valuable just by knowing that it's proportional to the concentration as grams per mil. Okay, and the molecular weights come from bouncing off of the calibration curve. Notice that I chose to draw this for a part of the curve, the black curve, that doesn't exactly match one of the elution volumes of my system, of my calibration system. So what I'm going to do is I'm going to come up here and I'm going to reflect off that curve. And that's going to give me the log of M. And then from the log of M, I can calculate what the molecular weight is. Okay. Well, here's the actual data collected by a friend at Dow Chemical. And by the way, Dow Chemical invented GPC. I was just learning to ski when they invented this, I think. So anyway, a long time ago. And you can see 1, 2, 3, 4, 5 different peaks came out. That is a single run of a cocktail. Okay, so this is a solution of the calibration standards, and they chose 5 of them and put them all in the same solution and trust the GPC to separate them. Because otherwise you would have to inject separately and make a separate run. There's a half an hour. 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 It takes about a half an hour to make a run. Or you could run the cocktail. You can make the cocktail and run them all 5 of them in a half an hour. And that's much faster, of course. Now you'll see some other points. Okay, so these are not run. We did not run these separately. Okay. We ran them once and we trust the machine to resolve them and do it all in one run. And then we identify the elution volume, just from reading the point. Just read the peak. That elution volume corresponded to whatever this molecular weight was, okay? And so that molecular weight is low. Try to do this parallel. Looks like, does that look like 3.4? Or what's 10 to the 3.4? Oh, I don't know. 2,500, 100 maybe? Somebody check that with their calculator. You can check that later, but that's probably close. All right. And then they wanted more points on their calibration curve, so they ran a second cocktail, which they didn't show you, but we could figure out what it looked like. It must have looked like this. There had to be a peak there that comes to this peak. Then there had to be a peak there, and we don't know if it was higher or lower. It doesn't even matter if it's higher or lower. Okay, and it looks like they ran. Oh my God, they must have great resolution to get these 2 points. Okay, and then they ran that one, and they ran that one. So that's 1, 2, 3, 4, 5, 6. Right. It could be they even ran 3 cocktails. We don't really know. But in the end, they come up with how many points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. And they form this calibration curve, which looks nice and linear. And you could say, well, I told you that it would have a different shape. I said earlier that it would come up like that, didn't I? Well, they just didn't run very high molecular weights in their calibration curve. They just didn't feel the need. Okay, they know approximately what molecular weight range they want. In industry, they're making polymers by the rail car full every 15 minutes, and that's a small chemical plant. And they will hit the target molecular weight plus or minus 5% or so. So very precise, very good chemical engineering goes into doing that. All right, so that is a 2 cocktails to create a calibration curve. And you can see that these guys decided to fit it to, looks like a cubic polynomial. You could probably make the argument that a straight line would have been just about good. And that's part of the uncertainty. What are you going to do? This is your call as a scientist. Is that really going to be a straight line, or is that a curve? You kind of have to wonder about that. All right, so this is a former student, and I'm recently again in contact with him. It's much fun. And he was, in those days, interested in cars, as I always am, and decided he wanted to come clean my car. No, he didn't decide to come clean my car. He bought a new red car, and he wanted to try a touch-up paint, but he didn't want to waste it on his car, so he thought he'd put it on mine, which is not as nice. I still have that car. It still has the Happy 098 license plate. I did not choose that license plate. They have a jokester in Louisiana who does license plates, and I'm pretty sure if you get something fun like an MR2 to drive, he puts a Happy 098 on it, happy 98% of the time. My son had a Saturn, and it is called IC 144, ICK 144, IC gross. And he didn't ask for that, it just happened. So I think they've got a prankster there in the licensing division. It's that kind of state. Anyway, that's Randy Cush, and he decided that the touch-up paint was okay. I still have that car, like I said. I think I'm going to try to equip it for electric operation now. And that'll be a blast to drive because it's a standard shift, of course. I'm going to keep that and have all the torque that goes with electric. Well, we'll see if I get around to that. Okay. The point of the slide is that you have to choose the right column to do this. If you have the columns that you buy are filled with these beads of polystyrene that are cross-linked. And when the cross-links are very far apart, then big molecules can go in and you have some hope of resolving them. And the cross-links are very close together, very heavily cross-linked beads, then that's not true. All the big ones will come out right away at the same resolution. So you have to choose them for the right pore size, okay? So just right is to have, the ability for some of the polymers in your sample to go through and some not to go through. And this requires some sort of a priori knowledge about your polymer sample, doesn't it? And the reality is that you just have to try something and see if it works. You try multiple things, and in industry they call that method development. And oh my God, they spend an awful lot of time on method development. Okay. All right. So you could ask, how did you get the molecular weights for the standards, right? Well, we have this idiot Dow manager, who by now must be retired or dead, telling us that you can't even do that. Well, of course you can't. And that information, the molecular weight from the standards, comes from osmometry or scattering or MALDI, which I told you about earlier, or analytical ultracentrifugation, which is really a cool experiment that we get to. We never get to it. One day maybe. Or what's called end group analysis. End group analysis is you can identify, usually in a polymer, the ends are different than the middle. You have an initiator on there, and sometimes you can pick that up spectroscopically and see it. It's hard to do for very large polymers. If you have one initiator followed by 100,000 of the monomer, that one initiator is going to have a fairly weak spectroscopic signal, and you might not be able to do that. But in any case, and for the purposes of this class, we're just going to emphasize that yes, you can measure molecular weights, and we're going to try to make it seem reasonable that you can do that. Okay, so osmometry is real science. It's tied to thermodynamics. It is an absolute method. Basically, it's the ideal gas law, written with an osmotic pressure instead of a pressure. So here we can just rearrange the ideal gas law, which is when it's osmotic pressure is actually called the Van 't Hoff law. Two F's? I don't know. Could be only one F. Definitely, there's two lumps on the W though. Van 't Hoff's law. Okay, and so the idea is you simply rearrange and you see that the osmotic pressure is CRT times 1 over molecular weight. That's all you would get, except there are always in polymers non-ideal terms. Polymers are hugely non-ideal, but that is another class. And the idea of the osmometer is simply that, you have this semi-permeable membrane which prevents the polymers on the right side of the chamber from getting into the left side of the chamber. They're too big to go. There's little tiny pores in this semi-permeable membrane. And the solvent can pass through, and when it does, it dilutes the polymer chains, which creates entropy. That's why it happens. And that also loads up this side of the chamber, but that builds up a pressure so that, eventually the drive to create entropy by diluting the polymers is balanced out by the extra pressure head on the right side. And so some osmometers originally actually worked just as shown. You actually just measured H that is a pretty slow process. And what's usually done now is to apply a pressure to the side that has the polymer and see how much pressure it takes to keep the solvent from flowing from left to right. But anyway, it's certainly possible to get a molecular weight from osmometry. Nobody does it anymore because light scattering gives that same information. And that's another class too. But anyway, but in light scattering, way it really works, we often think about it as light being, interacting with a particle, creating an oscillating dipole, being spread around. The way sort of that does happen, all that does happen, but a better way to look at it is often that it's zeroing in on small fluctuations in the concentration of the solution. So this is, X here is just some direction in a sample cell. It's just a test tube, and one direction of it is X. And C is the concentration of polymers, and you see I have a broken scale here. So, 0 is no polymers, and C is way high, but we just broke that scale so we could zero in and see that there are these tiny little thermally driven fluctuations. And I can actually represent this trace here by a Fourier series of waves. Okay, and that Fourier series of waves will have a component in the direction Q. Okay, so Q actually bisects the incident and scattering vector. I guess I can draw Q. So I can try to do that. Should be like here. Yeah, that's Q. It's not kind of a wiggly Q. But anyway, that's the idea of it. And then the characteristic distance of Q is 2 pi over Q. And so you're actually looking at concentration fluctuations on the scale of 2 pi over Q. And it works out that the light scattered intensity is actually how easy is actually, well, let's say the inverse of the light scattering intensity is a measure of how hard it is to stop the fluctuations from occurring. Okay, so this term here, d pi dc, this is how much pressure I have to exert on the system to make a fluctuation in concentration. If it's a lot of pressure, if that's very high, then the scattering intensity is low. Okay, and you can see that we have a JChem Ed article on this from a long time ago. But it makes sense because things that take a lot of effort to do, d pi dc large, means that it took a lot of pressure, it's a lot of energy to do it. If it takes a lot of effort to do it, in nature it just doesn't happen. Okay, that's what Boltzmann's law tells you. Anything that takes a lot of energy doesn't happen. And so if it doesn't happen, then there's not much light to scatter. If d pi dc is very large, these fluctuations up here would be very tiny. So let's call this one, d pi dc medium. And then d pi dc small is going to look like, if d pi d, if it takes little effort to do it, then d pi d, then they're going to have huge fluctuations. Okay, spontaneous fluctuations will be huge. So if d pi dc is small, then inverse of light scattered intensity is small. That means light scattering intensity is huge. Okay, it probably means you're near phase separation or something like that. All right, so that's how scattering works. And you also get one of the reasons that scattering took over from osmometry is it gives you this measure of size, and we sort of talked about that. A wave coming into a particle along the top ray can wind up destructively interfering with a ray coming into a particle along the bottom ray. So it's just slightly different distances in the path length of the two rays, and that can reduce the intensity. And that leads to this law here, which you know is the law of Ginyer. Okay. All right, so back to our gel permeation chromatography. What we do is we'll add a light scattering detector there. Actually, let's go back. That was our DRI detector. That's what we had there. Doesn't say it, but that's what it was. And we're going to move the DRI detector off to the right and insert a multi-angle light scattering detector, a MALS, multi-angle laser light scattering detector. And this is going to let us collect the light scattered off the sample as it comes out of the chromatograph. So it's going to actually get separated according to size, and then we'll be able to measure what that light scattered intensity is. We'll be able to convert that to molecular weight. To do that, we're going to need the concentration, but we're going to know that concentration because it's going to be measured by the DRI. All right. So you can see that there's some little problems here, though. The sample, we inject a little bit of a sample in here. Here it comes. That's our sample pulse that we inject in. And it starts getting spread out, big ones ahead. Now the big ones are really ahead. Okay. And so those big ones, they're going to hit over here. So here's the little ones. Go into the light scattering detector there. Okay. And so I've got the big ones in light scattering detector. Only one problem. They haven't hit the DRI yet, right? And so there's a lag here. There's a detector lag, inter-detector alignment must be performed. So what we're really going to do is we're going to pair, this DRI is going to give us the concentration, of course, right? So we're going to compare the intensity. Let's say we're going to get this intensity at, let's say, 20 minutes and let's say 10 seconds. Okay. I'm just making that up. We're going to compare the intensity there with the concentration at maybe 20 minutes and I don't know, 17.2 seconds. So we will align, we'll say there's a 7-second lag between the two detectors. It's much smaller than that, by the way. It's smaller than that. But you have to know that well. And that interdetector alignment thing is a big deal into making this GPC-MALS experiment work. Okay. So this is a waterfall plot. That's an old one. And it shows what you get, sort of a three-dimensional thing. We have multiple angles, so this is a low angle. And so that 16 over there must be high. This is a 16, I think this is an 18 channel detector. No, 16, it's a 16 channel detector. And we're only showing 4 to 16. And low 4 is the low angle because you can tell just by looking at it that the intensity is going down. If that was a mountain you were trying to climb down from the ridge, I just drew that line and you can see that it's trying to do that. I didn't draw it very well though. Do a better job. Yeah, there's the exact ridge. Okay. So, that's basically what you've got. This curve here, for that slice, this is called one slice. Okay. If we were to make that slice and make our scattering angle theta, and we put our intensity here. I just drew it. And we would have, 16 points across this. And I don't know if I'm going to get 16 here, it doesn't matter, okay? And so that's how your sample elutes, okay? The ones that came out early are the big ones, the ones that came out, so, this is the big side. Came out early, and this is the small side. Came out last, okay? And it makes sense. If you look at it, if we look at another slice here, let's look at this slice here. This is another slice. You can see that the intensity is lower, but more importantly, the slope is lower. So this is big. So this is, let's actually call this one, the first one, let's actually call it slice 395, say. I just made that up. And this is slice 437, who knows, okay. This is and then this is 437. But you see it's less steep, and so it means it's a smaller molecule, okay? And also the intercept is not as high. If we were to extrapolate back to zero scattering angle, which we can't quite do on this plot. But if we were, you can probably agree that the intercept is not as high. We combine that intercept with concentration information, and we're likely to find that not only is this guy smaller, but he's lighter and lower in molecular weight too. All right, so this is how it goes. This is a single slice, for one of them, and shows Rayleigh factor. This is that funny R in the articles that you have to read versus sine squared theta over 2. And the intercept gives a molecular weight of what, maybe 129,000, 130 it says there. The concentration here is low, okay? GPC works best when it has low concentrations, okay? It can't be too low, you have to have some to measure, but as soon as you have enough to measure quietly, you should stop, don't overload it. And then the slope of this thing gives us a size, see? So the intercept gives the weight, the slope gives the size from the law of Guinier. All right, so this is a recent result. That was the old result there. I don't even know if that was, but this is brand new. And a paper that we're putting out now on sodium polystyrene sulfonate. And it's a lovely bit of work by Paul Balding, who is the highest paid PhD graduate that I've ever had for starting salary. And moreover, he is living in a low cost of living area. He should be living like a king. Anyway, I think he's actually the highest I ever heard of in chemistry anyway. Sometimes you get engineers that are paid better, but usually only on the coasts. So anyway, this shows molecular weight versus elution time in panel A. There are some different polymers here, and you see that we have almost a continuous response of these things. And you can also show the radius in panel C and D. You can show the radius versus elution time. And sure enough, it goes down, and I can combine how fast the molecular weight is going with how fast the slope is going, and I can get the sort of Flory type exponents. Very nice feature of this paper that people rarely do is actually assemble the plots that you see along the bottom, real concentration versus molar mass plots. People sometimes did that in good old-fashioned straight GPC, which was the calibration type that I told you earlier. Okay. But for GPC mols, most people don't make these plots, and they really should because they're quite revealing. This is what you really want to know. And I forgot to tell you something that I'm going to tell you now. Why GPC mols? Why did we decide to add that concentration detector there? Well, until we did that, a straight GPC where you took a calibration sample and then you ran your unknown and then you backed it out. If your calibration standards are polystyrene and you happen to be measuring polystyrene, it works gangbusters. Okay. But if you have made a brand new polymer, the first person on the whole planet to ever make that polymer, let's call them polymer X. You don't have the calibration standards for polymer X. So what people used to do, and they should stop doing, they would calibrate with polystyrene because you can buy that standard material. And then they would run polymer X and they would say, well, we can't really measure the molecular weight of polymer X. They're like that Dow manager. Can't be done. All we can tell you is that polymer X has an equivalent polystyrene molecular weight of blah, blah, blah by GPC. So this concept of the polystyrene equivalent molecular weight got very popular because it's easy, it's fast, and it's lazy. But ultimately, people didn't want to do that anymore. And so once you have your mols detector on, you can get true molecular weights, absolute molecular weights, without actually having to calibrate anymore. See, I didn't really need to calibrate anymore to do the GPC mols. It's absolute. It's absolute. The other advantage to it is that if you have sticky polymers, that you're really not working by the desired size exclusion mechanism where the big ones come out first. That's a disaster too. And GPC mols kind of helps with that kind of problem. If you have polymers that are working by some combination of their size and their stickiness, how well they stick to the column material. All right, so here he's plotted the RMS radius versus the mass for polystyrene sulfonate, and you see several different polymers were combined, and they basically fall in the same log-log curve. And they give you basically the Flory exponent here that you expect. You expect, ooh, goodness, that's interesting. You expect, what do we expect here? We expect, goodness. We expect radius of gyration to be proportional to the molecular weight to the parameter nu Flory, right? And we expect nu Flory parameter to be 3/5, which is 0.6. Okay. And I think the very best calculations now say 0.588, but big deal, almost the same thing. So 0.62 is pretty close. What's missing here is we don't have pluses and minuses on these. But we do have numbers from different runs, and you can kind of guess what the idea is. It's plus or minus 0.01 or so. So pretty close. Then in the other panel, you see somewhat different results. CNAPs, these are commercially obtained NAPs polymers, and they're not as good actually. They come up with more like a slope of a half, or looks more like a theta solvent or some crazy thing like that, but that's not right. And the reason for that is that the commercial polymers are not pure NAPs. They are a significant amount of impurity to them. And the impurity is hydrophobic and causes the polymers to kind of shrink up on themselves, which is not good. All right, it's pretty common to have a shape parameter where you take the radius of gyration and divide it by the hydrodynamic radius. I did not show you this, but it is possible to attach to the GPC MALDs a GPC dynamic light scattering instrument. So where you can actually get the dynamic light scattering and get the hydrodynamic radius to go along with your radius of gyration. And so this information is of interest to people in theory who are interested about the flow of solvent past polymers, which is important for things like filtration and blood flow and so forth. All right. People also add, in some cases, a viscometer. So this would be GPC viscosity experiment. We would say GPC-Vis. And like I said, most people would now probably say SEC-Vis. And all of these things are called hyphenated techniques. So they're called GPC or SEC hyphenated techniques in chromatography. And this is valuable because sometimes you have a very weak scattering signal and it's hard to pick it up. The viscometer can pick that up pretty well. Sometimes they have a light scattering detector and sometimes they don't. It's important still to get the concentrations. It's kind of a complicated thing, and it's actually more complicated than I made it look here. But the idea is that you can measure those pressure drops and come up with viscosity. And since you know the viscosity, you know the concentration, then you can know, guess what, the intrinsic viscosity as a function of molecular weight. Okay. So this is a secondary method. I just want to point out that here is our Markov stack-Rada method again. The molecular weight that you come up with here comes from the intrinsic viscosity over the Markov K, all raised to the 1 over A parameters, okay? Right, and so this, relationships are pretty reliable. The data off these viscometers is plenty precise. So it's actually a pretty good method. And it leads to the idea of what's called universal calibration. And this is one of the most famous figures and one of the most famous papers in all of polymer science. Papers like 2 pages long, so I highly recommend you read it. When you read that paper, you're going to wonder, why are modern papers so verbose and long and meaningless? And this is short and to the point and means a ton. What they did was to inject all sorts of different kinds of polystyrene, regular polystyrene, polystyrene as a comb, so that's this kind of polymer, heterografted copolymer. They put in polymethyl methacrylate. They put in phenylsiloxane. They put in butadiene. So each of these points is a different kind of thing. Okay, and they measured the elution volume of them as they came out of the GPC. And they took the intrinsic viscosity and multiplied it by the molecular weight. And remember, a long time ago, we told you what intrinsic viscosity is, or at least what it's proportional to, is proportional to inverse of density, okay? So if I take intrinsic viscosity times the molecular weight, that is essentially volume, right? This is somehow proportional to R cubed, let's just call it volume. And so you see that all of these different polymers, different chemistries, different architectures, stars, combs, linear, grafted, non-grafted, whatever, they all fall basically on the same curve for that column. And so what that means is that you could make your molecular weight measurement, you could put your unknown in here, and let's suppose your unknown came out right there at, what is that, 24 and a half. Okay, so 24 and a half, it comes out here. And we read it off over here. We'll bounce it off of the calibration curve. And we don't get the molecular weight, we get intrinsic viscosity times the molecular weight. But we know, if we happen to know for that polymer the Markov parameters, then it's all good, right? We can convert intrinsic viscosity times molecular weight into molecular weight. So here's how that goes. Whatever comes out of the particular volume has the same product, intrinsic viscosity times mass. So let's let A be the polymer we're trying to analyze, and S be the standard. So we run our polystyrene standards. And we don't have standards for our polymer that we made that we want to analyze. We don't want to do the light scattering because it's too small or has DNDC of 0, or there's some other problem. Maybe we just don't have that equipment. Who knows? Okay. But we have polystyrene standards. We know that Markov coefficient. We have our material. If we're smart, we'll get the Markov coefficient for our material. And then we can calculate just by saying, well, what's constant is, we have anything the analyte comes out at a particular elution volume, I can relate that to its intrinsic viscosity times its mass. And so I can actually determine the mass of the analyte just by knowing the various Markov parameters for the solvent and for the standard and my polymer that I want to analyze. And so this is so good that I would almost consider it, it's almost like an absolute molecular weight. It's not. It's quite reliable. And this universal calibration idea has a lot of adherents out there in the community, people who really go for it. You do have to know the Markov coefficients of both materials. So at some point, you have to determine those, okay? But then you have, once you know that, if you're given an unknown material, an unknown sample of poly X, if you know Markov coefficients for X and for the standard, you're good to go. You don't need to do the light scattering thing. All right, I want to talk about problems with GPC, okay? And I started, I showed this slide for a long time, and some people know that those are the original Star Trek cast, And what I find is that people don't know that anymore. Not a lot of them don't. But that's William Shatner, and now you see him on late night TV commercials hawking sleep apnea equipment. That's his latest thing. If you watch late night TV, you'll see him. Leonard Nimoy and her. I'm afraid I've forgotten her actual name. The radio operator, Star Trek. But anyway, so then we had Star Trek Next Generation, and people don't know that. And then we had, in Star Wars in May 1977, we had, Harrison Ford, Carrie Fisher, and Mark Hamill were the stars. Everybody wanted to have little pin cushions on their ears like Carrie Fisher had. Kind of looked dumb. And you see how much they aged. This is, 11 years after the invention of GPC. GPC was 65 type of thing. Okay. So it's been around a long time. And one might think that something would come along and knock it off the block, but it really hasn't. That's despite the fact that it has enormous problems. There's just problems with this thing. Okay. And this is an old exploding diagram for a Waters GPC pump. And oh my God, these things were a nightmare. New pumps are better, and this is a result of better material science. It's kind of cool. But they're still a pain in the neck, and you still have downtimes of weeks or so to get them fixed. In industry, they will usually have a service contract, so you won't have to fix them. But if you really want to know what's going on, you need to be able to dive into these machines, and that's why you get the good job. You go off and do an internship with TOSO, like Luke Lee did, and really learn these machines very well. Or you go visit our friend down at LSU, Rafael Cueto, who's been doing this for maybe 45 years or so. He really knows. But that's a lot of parts, and you got to keep all those stupid parts, and they all have to work. It's a nightmare. It's a nightmare. Okay. So even if it's working, we have other problems. Question. You want to run some dextran samples. You're you're working with the biorefinery, and I hope these guys will come work with us one day, but hopefully they will, and they'll send us some dextrams to measure. And they want to measure them in 50 millimolar salt in the morning, but then in the afternoon, we want to change that salt to 100 millimolar salt. Can we do that? Probably not, okay? Because it takes the differential refractive index detector forever to restabilize. People say line out. Okay, so if you're running 50 millimolar at 10 a.m. and you switch it over maybe at noon for lunch to 100 millimolar salt for some other polymer, a pretty good chance it's not going to be ready by 2 p.m. What if you wanted to make a measurement at 45 degrees at 8 in the morning and then 50 degrees, only 5 degrees difference at noon? No. Again, the DRI detector probably will not have lined out well enough to do that. I once visited a giant GPC facility at Shell's West Hollow, Texas research facility. And in that room, they had 60 instruments, 60 pumps, 60 sets of columns, 60 DRI detectors, 60 injectors, everything, all automated, all by computer. And each GPC instrument is a huge room. Each GPC instrument had a sign in front of it. And they would say typically THF, room temperature. The next one would say THF, 40 degrees. A whole other machine just to change the temperature, right? Can't go much higher in THF, it'll start boiling, so we'll go to xylene. Here's xylene at 30 degrees, another machine for xylene at 60 degrees, another machine for xylene at 80 degrees. Then we would have trichlorobenzene, a whole series of those, 3 different temperatures for trichlorobenzene, 60 machines, all with different labels for different conditions because it's such a pain in the neck to change the condition. So obviously we're not going to do that. Talked a little bit about non-size exclusion mechanisms binding. GPC-MALS helps with that, okay? So the solution to that is GPC-MALS, but it doesn't always work. I mean, sometimes you put something on your column and it doesn't come off, period, ever, okay? And you might have ruined somebody's column, and columns are expensive. They're like $1,000 a piece. 30 minutes per sample, okay? When you do high temperature solvents, it's no fun. Calibrating doesn't tell you anything. You have to calibrate. If you're doing straight GPC, you have to actually calibrate. All you get out of a GPC calibration curve is the log of molecular weight versus the elution volume. There is no more fundamental information to be had, I assert. Could be that real people like Andre Striegel, who really do this at NIST, might disagree with that, but I think there's really nothing to be gained by calibrating. All right, already mentioned expensive columns. So we began to wonder in our group if you have to separate polymers to get them sized, okay? So I took this picture, when is this? April 1, April Fool's Day, 4:11 a.m. Well, it's only 2:11 in Colorado, that's where I was then, I think. So anyway, this is a picture of someplace in Atlanta. Oh, it's near Georgia Tech. And let's suppose that a car is speeding. In the past, we had to separate that cars from all the other cars, right? And that means we would turn on the flashing blue lights and pull them over and write them a ticket, right? We had to separate them from the others to give them the citation that says, hey, you're speeding. Well, you know, you don't have to do that anymore, right? You just have the camera take a picture of the license plate and send them the speeding ticket in the mail, okay? So it's really not important to pull things over and separate them in order to get what you want. And so in GPC, you actually do. You actually separate the big ones from the little ones, the fast big ones from the little small ones. And then you tag them for molecular weight using light scattering or something else later on. You don't have to do that. So we have this technique, which in our lab is called matrix fluorescence photo-bleaching recovery. It's designed to compete with GPC. And here it is actually working. What happens here is instead of actually flowing the sample through anything, we simply measure the diffusion coefficients of the whole matrix, of the whole polydispersed mixture. We just measure those diffusion coefficients. And we can convert that to a molecular weight, and it has almost GPC-like resolution. This is actually pretty good. And so this is an application. It's a little bit like dynamic light scattering applied to a polydispersed sample, but it has much better resolution than dynamic light scattering because we're forcing the molecules to diffuse through some other molecules. Okay, if they just have to diffuse in solvent, yeah, the big ones go slower, and that's something. But if you make them diffuse through a matrix of other materials, then the big ones really go slower, and you get better resolution. Okay, so goals continue. This whole methods development things. Everybody would like to have black box for molecular weight distributions. Here are some of the characteristics that we see. DOSI is an NMR technique, dynamic light scattering. You've seen about a little bit. They all have pluses and minuses, but I really kind of think I'll go back and look at this matrix FPR thing again because we can, as we did it, it was sort of a big, bulky, expensive thing, but I think it'd be now possible to miniaturize that. All right, search continues. We're going to discuss some promising things that are already happening. MALDI and field flow fractionation. I'm going to go fast through these, so you're not going to actually do those. This is you could get a much better YouTube on MALDI, I'm sure, than this, but the basic idea of it is simple enough. You put your sample in this, you take your polymer that you have. It doesn't take too many molecules either. You take your polymer that you have and you mix it with what's called a matrix. And the matrix is chemical. It's usually a dye. It's a dye that's designed to absorb this laser light. And you blast the matrix and the molecules that you've dispersed in the matrix with this dye. The dye absorbs the light. Temperature goes like from 0 to 10,000 degrees in almost no time at all. But you're working in a vacuum, and for reasons that I don't know if anybody really understands, the molecules mostly hang together during all that. And they ionize, okay, but they don't usually break. And then you accelerate the ions with a electric field, and they come out according to their size. So they hit the detector over here as ions. We have an ion detector here, and the molecule hits it, and they are separated according to their size. Well, a laser flash can be timed, I don't know, to nanoseconds, picoseconds even, right? So that's high resolution. And then these detector spikes here can be timed pretty well. So when the sample hits the detector. If one molecule hits a detector a millisecond after the previous one did, it's no problem. It resolves that okay. And so the answer, what these things come out looking like is this. You have photo counts. Here's number of molecules here. I call them photo counts. I should call them molecule counts. This is how many molecules were counted as a function of their mass. And this is phenomenal resolution. This is phenomenal resolution, okay? And here you actually do see the discrete nature of the molecules. So if it was polystyrene, that top peak there would be 104 molecular weight units, different from the one just a little bit to the right, which would be another. So these gaps between the peaks would be the monomer molecular weight. Okay? And you can do more than that. You could actually analyze, the mass of that thing is going to be, let's just pick one. Let's just pick what this mass is going to be. Okay, there's that mass, that peak. Okay. The mass of that is going to be, boy, looks like, did we crash it? Not really. I don't think we crashed it. I just think it died temporarily, got out. I believe it'll be here when I get down there. But I don't know if I'll be able to write this equation. That's hard to say. Okay, so this mass of that peak, so the mass that's on the x-axis here, is going to be the initiator mass plus the degree of polymerization dP times the monomer mass, right? That's the idea of it. Sometimes you lose or you add a sodium or something like that because you pick up a sodium atom from someplace. But the point is that you get, you can even tell how the polymer was initiated. You can get an idea what the molecular weight of the initiator is. And the gap between these things, the gap in between the two, and there it goes again. Guess I just can't avoid doing that. The gap between the peaks is the monomer mass. Incredible precision. Okay, the mass spec people are really, really good at this, and it's often used for proteins, but it works on macromolecules too. And this one is actually as you can see, a pretty low molecular weight polymer. And we know that the polydispersity parameter, dispersity that we use to describe these distributions, is 1 for monodispersed. This is what 1.05 looks like. Okay, so usually if you ran something that was this is pretty nearly monodispersed. One single peak would be truly monodispersed. Nature does that. This is pretty good for a man-made polymer. It's kind of a humbling thing to think about. Okay, so molecular weight is about 1.05. All right, so you know, there's a lot of interest. Polymers is very related to particles, and there's a lot of interest in particles. So instead of throwing a dog and a cow in, let's suppose we throw two big things in, a cow and an elephant. Now, neither one can get into the quiet zone of the branches, okay? So they're really hopeless for them. You think that GPC is just not going to separate those at all. The dog and the cow and the elephant are going to come out at exactly the same time. They're going to flow right down the middle of the river, and they're going to come out at exactly the same time. No resolution at all, none, zero. All right, but there is a solution to that, and the solution is called field flow fractionation. And the idea of it is instead of a column, now you have this sort of slab-shaped thing, channel, and it doesn't really show the scale here very well. But I think this is typically, I guess I'm going to give you some questionable information here. I think this is about 100 microns. Put a question mark on that, okay? It varies. And what you do is you actually put your sample in it, and actually the sample all will start off focused here, like that. And then it'll flow down this channel. And what happens is that the big ones get stuck early on, and the little ones come out first. So that's the main thing to know, is it's the opposite of GPC. Little ones come out first. But the question is why? And this has to do with how this thing is constructed. What we're going to do is we're going to put in, I don't know what the units will be, but we're going to put in 100 units of solvent here at the inflow. And at the outflow, we're going to allow 95 units of solvent. Now, solvents are incompressible, but luckily for us, the bottom of this channel is coated with a membrane that allows the extra water to escape. And so that really creates, the overall flow field is down the channel, but it really creates a kind of a downward pressure. on the molecules, and the big molecules feel it first, and they get pinned down on the bottom of this chamber, okay? So when I was a kid, we didn't have anything to do, you know, we would go out to the barn and, you know, try to get a butterfly or a moth or even a housefly to land on our hands. And then if you can get that to happen, you can blow on it and it can't take off, okay? So if you blow hard enough, you can even hold a housefly on your hand. I don't recommend it because they might bite you. You know, it's them anyway. But it's very handy if you're wanting to study butterflies. You can get them to land on you, and they can't flap their wings hard enough to get up. Well, it's the same kind of process here, where the crossflow pushes the big molecules down. Of course, it's again like an osmometer in the sense because you have the semi-permeable membrane. If the membrane pores are too big, your small things might go through it, and that's not good. But anyway, this really works great. And you have a lot of tunability in this technique. You can change how much cross flow you apply. And if you inject something that's, you know, potentially damaging to a GPC column, all that's going to happen here is you might ruin one membrane, but they're easily replaced. They're not nearly as expensive as a GPC column, and they're pretty durable. So you know, it's a lot safer for running weird samples, and it goes to very large things. That's the main point. And it works great from, you know, basically from dogs all the way to elephants or even whales. I never saw anybody put a bowling ball down one of these AF4 instruments, but you know, any normal sized colloidal particles really can be measured all the way to proteins. It's a fabulous method. Okay, so the advantages of field flow fractionation is it handles a wider range of particles. I think it might be easier for some really weird solvents. Here's an example of some polytetrafluoroethylene latex. You guys have now made latex particles, some of you anyway, I think. And this is what latex looks like for Teflon. It's often sold as a latex dispersion. And you can see how well we size that. It's really quite good. A light scattering detector was hooked onto this thing at the same size. And you can see the red curve for that. And you can see that indeed, the little ones are coming out first. The big ones come out later. It's the opposite of GPC. GPC is essential to any nano lab, any polymer lab. I keep thinking GPC could get replaced either by something like a black box like matrix FPR or field flow fractionation, but the thing just keeps hanging on. It does have a life of its own, it seems. And with that, I've reached the end. And looks like I'm a little bit long, so you will probably be paying this at a little bit of fan speed, and that will work out okay, I guess. That's all I can do. Thank you.